All right, so now let's take a look at the frequency domain of this sampled signal. So we actually want to have a discrete or perspective from the discrete domain for frequency domain analysis. So what we're talking about here is the discretized signal versus the actual discrete signal. So remember that the discretized signal is still continuous. So in the time domain, we had our original signal with some spectrum. Then we went to the sampled version, which is still in the continuous domain, and it has a spectrum which has multiple copies. Where they are depends on the sampling frequency. Now we want to consider what happens when we actually go to the discrete domain, the discrete signal. That is our vector in MATLAB speak, or our array of amplitude values. And how do we analyze that in the frequency domain? Well, you may remember we took a look at such signals in the time domain way back when, and we talked about this normalized frequency, capital omega. And that's where we're going to be going with this. So in the continuous domain, the frequency in the continuous realm, the frequencies are represented by individual phasors like this at certain frequencies omega naught or k omega naught. In the discrete domain, we're going to be dealing with this normalized frequency and n. So normalized frequency instead of frequency, and n instead of t. Okay, so in general we could have any discrete time signal, but we're going to look at both periodic versions and non-periodic. So remember that a periodic discrete time signal has some integer n after which it repeats itself. And that is going to have what's called a discrete time Fourier series. Okay, but we could also have non-periodic discrete time signals. So there is no integer which makes x of n repeat itself. And for that, we are going to actually have a discrete time Fourier transform. So hopefully you're starting to see the analogies here. And then there's actually something called a discrete Fourier transform, and we're going to talk a little bit about each of these. We're going to focus on the top two. So the discrete time Fourier series has discrete times n and discrete frequencies k. The discrete time Fourier transform has discrete times n, but it has continuous frequencies omega. And the discrete Fourier transform is sort of this is basically what you have to do on a computer. You have discrete times n and discrete frequencies k, but this allows us to capture non-periodic signals. So we're going to focus on discrete periodic signals first, and in particular the discrete time Fourier series. So this is sort of the path in the hierarchy that we're going to be taking a look at. Okay, so recall that a discrete signal is not necessarily periodic, even if it was sampled from a periodic continuous time signal x of t. So there has to be some integer n for the discrete signal to be periodic. We took a look at that probably about a month ago. As we did with the Fourier series, we'll just assume at this point that we start with such a discrete periodic signal. So there is some integer n such that x of n is periodic. So if x of n is periodic, then we're going to assume that we can write it as a series, a summation, and what we're going to use for those basis functions, just like we did with Fourier series, is these exponentials here. Okay, so these are our basis functions for a discrete time Fourier series representation of a of a discrete time signal. And omega k is normalized frequency. So just remember that that is unitless. So the question is, how should we choose those omega, those frequencies, so that it is representing a periodic signal? And how many functions do we actually need? Okay, so those are our basis functions, those are the normalized frequencies. Let's answer the first question. How should those be chosen? Okay, well, if our original signal is periodic, then we should expect that we want our component basis functions to also be periodic with the same period, capital N. So we want this requirement to be a constraint on our basis functions. And if we expand that out, we'll get this. And for the left-hand side to equal this right-hand side, we want this to equal 1. So that is our constraint on omega. That is going to happen whenever omega k, capital N, is an integer multiple of 2 pi. And therefore, our frequencies are 2 pi k over capital N. So k is representing our frequency, n is the period. And so this gives us the discrete time Fourier series representation of our discrete signal x of n. So note that there is a k in here and there is an n in here. N is the analogy of time, k is the analogy of frequency. Now, how many basis functions are needed? Now, in the continuous time Fourier series, we actually needed an infinite number of them to reproduce our signal. But think about what happens if we add capital N to our basis function. So what does it do to it? Well, k just becomes k plus capital N. But we can separate that out into the k part and the capital N part. And what we get over here is just e to the j 2 pi n. Well, that is always equal to 1. So what we thought was maybe a new basis function actually just turns out to be one of the basis functions we've already used. And so there's actually no point in taking our discrete time Fourier series out to infinity in both directions, because we're getting redundant information. Those basis functions are not actually adding any new information. So our discrete time Fourier series can actually start at 0 and go to n minus 1. Or in other words, we only need n terms. Okay. So this is basically a summary of the discrete time Fourier series, and it is telling us that we can reconstruct any digitized signal as a sum of Fourier components that are like this. This expression tells us how to find the coefficients for each of those components. And if you think about how that relates to our continuous time Fourier series, there's a direct analogy. Now the only difference is, or one of the differences is that in continuous time we actually need to take those sums to infinity. Here we only need to take n of them. But note that this expression and this expression for the coefficients are actually very similar to each other. So note that we're using n instead of t, and we have a sum instead of an integral. Capital N is the period, t is the period, so there's some an analogy between those as well.